So as I said, so people will have it in the recording, so that you can remember this. So as I said, we are a community, you and I, and the TA. And then, if we want to progress together and learn together, we will have to give our opinions and feedback to each other. So this is why I am setting up this 3-to-1 survey. So what does this mean? So you will see it will be available online. So you will have to cite 3 things that you learn, you like, you're excited about, 2 things that or questions or you haven't learned about, etc. And 1 thing that, or 1 question that hasn't been answered, or 1 thing that you are worried about. So, giving your feedback it's a part of your participation. So this is why I put it in red. You don't have to give positive feedback to make me happy. It's you. I want to encourage you to be confident to give a feedback. So be confident. These are feedback constructive. So when I give you a feedback, it has nothing to be personal. When I say, you have to progress in this, when I emailed you about your question, assignment questions, and I said, no, you need to do this, you need to do this, it has nothing to be personal. It's for you, for your benefit. Same thing. If you give your feedback, it's for your benefit. First, you will be learning to criticize in a way because you won't be a student for your entire life. You will go to work, you will go to grad school, go to med school, etc. So if you don't gain this confidence from now, it will be very hard to do it. I'm telling you from my own experience. So this is why. The assignment, the survey won't be anonymous, so I will know who said what. And people, I don't want to point, people, some are here, some are not. I met with few of you a few days ago, and some said, we didn't like this and that. People who are here and who will hear the recording, thanks to you for giving me these feedbacks and giving me this opinion. So for example, someone told me that they didn't really like the tutorial. They were expecting this and that, which I really appreciate, and I really respect these people. Others, they said, oh, we like it, etc. So it depends. You don't have to like everything, and you cannot like everything, you cannot dislike everything. So as I said, we are a community, and we should act together as a community. So if you give me feedback saying, I need to do this, I haven't learned this, or I'm expecting to do this. So we still have time, and we still have other tutorials, etc. So me, as a prof, I can adjust based on your feedback. So this is the purpose of the 3-to-1 survey. I don't know, I'm not sure if you have seen this before, but it may come in other classes or other courses. So as I said, this counts as your engagement and participation. Please, I don't want to see all positive feedbacks, as I say. How to say it? Give constructive feedback. And it's okay. You don't have to write like really very well written, English written sentence, etc. That's okay. You just give your opinion as you feel it and as you say it. So this is the thing. To encourage you, should me say this? So as a bonus for people who will be completing the survey, I will be giving 0.5. It doesn't mean negative, positive. You just say, oh, we like it. No, I need a constructive. I need something, you will see it. You have to cite something positive and you have to cite something negative. So As a bonus, I will give 0.5 extra to the term test. So, for example, for someone who got 27.5, will get 28, and so on, out of 30, obviously. So 0.5, it means something because it counts for 0.4 of the final grade. So this is why I don't think it's something more motivating than this. Okay. Then next week we'll have a lecture on lipids. So it will be mainly how to process, how to make oil, basically how to do the hydrogenation, etc. So like mainly processing about commercially important fats and oils and how to process them and how to manufacture them. So, and we will have a tutorial, if you remember, if you go to your syllabus, we'll have a tutorial on how to identify, how to read the labeling, or how to read the list of ingredients, and how to identify emulsifier, and maybe we can have some additives. So we'll have fun next week as well, I hope. So for this, I have two options. So first option, so we'll go the same as the last time. So we do first 60 minutes or 70, 80 minutes will be dedicated to the lecture. Then we'll have a break, and then we go to the tutorial. Or there is another option. I will be recording the grades, posting them online. But you have to, because you have to like learn and listen to the recording, obviously, because these will be included in the exam. And then, so if we do this, we will have 3 hours, probably less than 3 hours. We'll do the tutorial, and we will be discussing other topics based. So you'll be the one choosing the topics. So, for example, for the one working on chocolate, is Jenny here? Okay. So for the one working on chocolate, so they can, for example, share their idea about chocolate or what they have learned about chocolate. For the one who work on chicken, I know there are so many working on chicken, etc., etc. So you guys will be leading discussion. So this will help, as I said, you. It's kind of a training to have an oral presentation, being confident, talking in a community, etc. So my objective is to help you progress in a way that is more motivating. So yes, I'm here to give you lectures, but I want you to enjoy. I want you to enjoy the lecture, and like I hope that I can transfer this positive and this. I'm so motivated, and I'm very happy to come here and teach this course. Teaching this course means a lot to me. So this is why I hope that I can share this positive energy with you, or I can transmit it to you. So survey will be available online, and I have already created. We'll post it later on the discussion. I have already created a link on menti.com. So this is the code. We'll post it later, and so then you can vote. So please vote if you choose the first option or you choose the second option. Okay, so let's start. Today's lecture is about lipid, and as I said, I really like this lecture. It goes from very basic to more application, etc. So today we'll be learning together or having like a refresher about chemical composition. Then we'll go to interesterification. We'll talk about emulsions and emulsifier. I will go real quickly just to give you the basics, but next week we'll be practicing about this. We'll talk about fat replacers and section. And section 5 about rancidity and lipid oxidation. So when I put this in the first slide or second slide, this is kind of another way for me to tell you the learning objective of this section of this lecture. So instead of writing learning objective, etc., I prefer putting it this way. So let's start with the first one. I should get a pointer so that instead of coming back and forth. Okay, so when we talk about lipids, we can distinguish between oils and fat. Oils usually, they are liquid, and fats are solid. So I put them between brackets or asterisks because solids can also be a blend of liquid and solid fats. So it's a mixture. We'll see probably later. So this, why? Because this is due to the variation or the variability in the triglycerol composition. Because there is a heterogeneity in this triglycerol, this is why there is a blend. And this, when we have a blend of solid and liquid, and this is what usually we call semi-solid. I added, you don't have semi-solid in your slides. And what we call plastic fat. So plastic fat is a combination or a blend between liquid and solid. When we have liquids, we can distinguish them based on their composition. So we have fatty acids. We have mono and diglyceride. Glycerol, so these are mono and form the mono and diglycerides. We have phospholipids, so these are the most component of the emulsifiers. We have the triglycerides, and these are the fat and the oil. These are what are present mostly in food. And as I said, so these glycerides and phospholipids, these are what they compose, or they're considered or used as emulsifiers because of their structures. When we talk about fatty acids, these fatty acids vary or change based on their structure. So these are part of the triglyceride. So we'll see it in 2 slides. This is a refresher. You have seen this in chemistry courses. So these are esters of glycerols and fatty acids. So we have a glycerol backbone, and we have the 3 fatty acids. So these are the main mainly present, mainly composing or mainly present in the food, and they can be present as within the food matrix, or we can also have free fatty acids. And then free fatty acids, their presence is an indicator of spoiled food. So when we have a spoilage, or acidity or other spoilages, we can just measure. There are different ways of measuring fatty acid, and this is how we can see the spoilage or detect the spoilage. The fatty acid change based on their length. So we have C18, C6, C12, etc. Number of carbons. They differ or vary based on their presence or absence of a double bond. So they can be either saturated or unsaturated, saturated fatty acid or unsaturated. The number of and the composition of double bonds. So either we have monounsaturated or polyunsaturated fatty acids. And obviously, when we talk about unsaturated, we will talk about trans and cis configuration. So when we have saturated, so meaning there is a 0 double bond, so this is the way how we identify them. So saturated fatty acids, how we can distinguish them? We'll distinguish them based on the number or the length of their chain. So if you can see here, so we have C4, 0. 0 means 0 double bond, so it's saturated. C4 meaning it has it has 4 carbons. And then, so these are the systematic. So this is the chemical, how in chemistry we do it, we name them. And this is how we name them, like commonly we name them. It's a common name. So for example, the one 4 carbons, it is a butanoic acid. But then it's commonly known as a butyric acid. And sometimes we call it butyrate. Capric, lauric, meseric, palmitic acid, or palmitate. Palmitic acid is the most common one. acetic acid, etc. And then here in bolded, so this is how we, these are the abbreviations. So B for butyrate, P for palmitic, ST for steroid, etc. And then usually when we are working commonly, you don't have to remember this. But then for people who work frequently with these, you have to remember. So when you see ST is a steroid, when you see P is palmitic, etc. Same for the unsaturated. So when we have unsaturated, we distinguish them based on the length, same as saturated, but also based on the number of double bond and the position of a double bond. For example, same here, we have systemic name and the common name. So when we have, for example, C16-1, meaning we have 16 carbon, it's a chain of 16 carbons, and there is a one unsaturation. So usually the unsaturation, so when we have one unsaturation, and then usually it's written, it tells you where is the insaturation, where is the presence. So here, for example, the first line, we have 9 hexadecanoic. So the 9 meaning the position of a double bond, it's at a carbon 9 counting from the carboxyl, so from the COO. Because we can count from the metal part and for the carboxyl COOH part. So if we count from the COO, it's a position 9. We'll see it in the next slide. But if we count, so this is systemic name. But then common name, usually we count from the methyl group. And this is what we call the omega, or omega naming. I added the text box as you don't have it in your slides. So, for example, same example. Here we have C16-1, 16 carbon, 1 in saturation. It is located at omega 7. So this is an omega 7. So it's located at carbon number 7. And this is what we call, for example, omega 3, omega 6, because they are at carbon 6 and carbon 3. When there is no name here, for example, all these, they are assumed to be cis. So they have a cis configuration, unless it is indicated. If, for example, you see C12-113, this one is a cis configuration. If it was a trans configuration, you should have seen trans written beside. So this is how we identify between them. Unsaturated fatty acids, so in terms of health, they are good for health compared to saturated fatty acids. But they are very reactive. So the reactivity, they react with the oxygen and other components easily. So the reactive, so this is why they're easily degraded or easily oxidated compared to saturated. So the reactivity is higher in unsaturated compared to the saturated. In saturated, there is no free radicals and no free components to react with. And so they're easily oxidated, and this is what leads to the rancidity. So the rancidity is the defectuous taste and odor of the oil or the fat. So this is to recapitulate. So this is how we count. So we either count from the methyl group, or we count from the carboxyl group. So for example, we have in the top an example of omega-3. So it's the C18. If we count, so if we count from the carboxyl COH here, the double bond should be at 12. Here, if we count from the methyl, the double bond should start at carbon. What's this? 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14, 15. Yeah, at 15. And then the omega-3, because it's the methyl this way, so this red, this is how we count it. So this is the omega-3. Same example for the omega-6. Configuration, if you remember I said there is a trans and there is a cis configuration. You have seen this so many times, I know. So we have a cis configuration. So we have the H one side and then the component the other side. And we have the H here that is inverted, or like the configuration is at the opposite from the both sides of the double bond. So this is what we call the trans. And then trans, if you remember from the first lecture, we said they're associated with some health adverse effects. And then trans fat have been banned from the market, from the Canadian market about a few years ago. Okay. When we talk about lipids, we can characterize them, can distinguish them based on the physical properties. So here, mostly when we cite these properties, it says physical properties, but they should be considered as chemical, physical, or chemical properties, because these are like based on mainly, yes, we're talking about physical composition, etc., but we're also talking about chemical reactions, etc. So this is why I prefer, you may find in books, physical properties. Some they say chemical properties. This is just to tell you. So when we talk about this, we will talk about saponification value. So this is a value or a technique to help us determining or identifying or measuring the molecular weight of fat or lipids. We have the iodine values. They help us indirectly determining the degree of insaturation. We'll see it in a few slides. And you may have seen, I'm skipping, I skipped a few slides. No, I didn't skip, so like they're hidden in my PowerPoint, but you have them. So these are extra slides. So these are just for you to, when I say extra slide, this is just kind of a refresher. This is why I'm not showing them here. It's just for you, extra slide for you. Then we'll be talking about melting points. So the transition from solid to a liquid. This is a very important property for lipid. We'll talk about, when we talk about properties, it's very important to consider the distribution of the triglycerides, so mainly the distribution and the position of fatty acid within the backbone, and the crystallinity. Yes, lipids can form crystals, the same as water. Same, I didn't show it here, but it's the same. So the nucleation and then the propagation, etc. So the crystallization of the lipid is different. So it's, it doesn't have to be at -1 or 20, etc., to form crystals. Crystallization of lipid can happen at different temperature depending on the melting temperature of the fatty acid. Okay, let's start about the saponification. What does this mean? So by definition, it is a process involving the hydrolysis of fats, the triglycerides, on its reaction with the alkase, which leads to the formation of glycerol and salt of fatty acid. What does this mean? So we have a fat, triglyceride, here. So we have, and then it is hydrolyzed in presence of an alkylase. So here, in this case, we have the KOH, so potassium hydroxide. It can also be sodium hydroxide, NaOH. So you may see sodium hydroxide. And which this hydrolysis will lead to the formation of glycerol. So you can see here, like there is a hydrolysis of the ester formation, and then a formation of specific product that is called a salt of fatty acid. Here, because we're using potassium, we call it potassium salt of fatty acid. And what is this? It's simply a soap. So this precipitate, or potassium salt, or salt of fatty acid, these are soap. Has anyone tried to make soap at home? I haven't, but I know someone who does it. So you can mix olive oil with sodium hydroxide, heat it, and you kind of, then with this precipitation, you kind of have this, you put it in mold, and you can have your own soap. I have never tried, but maybe one day I should try. Okay, so as I said, the saponification is a way to characterize or to measure the triglyceride. Why? Because it is known that to make soap, we need a specific amount, or to make soap or to saponify, we may need a specific amount that is measured by milligrams, so a specific amount of KOH, an alkali, either KOH or NOH, to saponify 1 gram. So this is how we measure. So milligram of KOH or NOH to saponify 1 gram of fat or of oil. And then, because of these, so these are titration. So we put our glycerol, so we start adding the KOH until we have this glycerol formation, and etc. So it's easy to measure the quantity of KOH or NOH added, and then there is a specific formulation, and we can identify the numbers. So there is an association between the amount of KOH added and the saponification value and the molecular weight of these triglycerides. So let's have this example. So for example, we have two products with equal weight of fat, so equal amount of fat. So first we have two triglycerides. Let's say the fatty acid, the chain of fatty acid has 6 carbons each. The second one, there is 1 molecule of fatty acid, and then 1 molecule of TAG, and the length of the fatty acid chain is, let's say, what did we say first? 6 carbons? The top one. Let's say each bar is a fatty acid. So the top one, the bars, they have fatty acid of 6 carbons. The lower ones, they have a fatty acid of 12 carbons. So if we count the number of carbons, the total number of carbons, etc., it is the same. But the molecular weight of each individual triglyceride is different. So here, for example, here when I was drawing it, so I remember I drew it with 1.8 centimeter, and the other one 0.9 centimeter, just to show you that this is half of, the top one should be half of this. Yes, we have same number of molecular weight. For both of them, we need a specific amount of KOH to saponify 1 gram or 5 gram or etc. of this specific fat. For the first one, the top one, we need enough KOH or NOH to hydrolyze 6 ester linkages. So we have 6 because we have 2 molecules of triglyceride, and then so there are 6 linkages of ester. So we need to break the 6 linkages. So this is why we need enough amount. So doing this, we will consume more KOH, or if we use NOH, we will consume more compared to this one. Because here we only have 3 ester linkages, and then the top one we have 6. So yes, the weight is the same, but the amount required depends on the molecular weight. So And it is known that lower molecular weight of a fatty acid, the more you need KOH. So the top one is you have lower molecular weight, you need more KOH to saponify, and that this is considered as a higher saponification value. So saponification is inversely related or inversely associated with the molecular weight. Higher molecular weight, lower saponification, and etc. We'll see examples so that you can remember. So why do we need this? Yes. So we identify this. We identify the molecular weight, but why? How it's used? This technique or this saponification value or this specific properties of lipid. So in addition to identifying or determining molecular weight, because there is, as I said, there is a specific formula. There is a number of milligram per gram. So if we know a number of milligram, we can identify, and then vice versa. And then if you go in, like there are charts. So it is known, for example, I don't know, milk fat, we'll see it soon here in this slide, has a range of specific fatty acid, specific saponification. Vegetable oil. So most of the vegetables, they have a known range of saponification value. So for example, if you're working in quality control lab, you don't have to do it every time. So you have a chart, and then if you are controlling different products, so you have a chart, and then you do your titration, and then you go to your chart to see where to compare your values and to can identify the molecular weight or identify the products. So this saponification is important because it's used for the detection of adulteration of dairy products with cheaper fat and oil. Milk fats are considered as, you may be surprised, as expensive fats. Yeah, put it this way. So milk fats are expensive in terms of like amount produced and so etc. So when milk is collected from farmers, so usually it's set. So for example, if the farmers collect milk, cow milk or other animal milks, so if they let it sit for a specific time, there is a separation between milk is an emulsion. So there is a separation between fat layer and the liquid layer. And it's easy to collect the fat from the milk and use it and sell it. So for example, farmers can do it. So they sell the free fat milk, and they can sell the butter alone. And because the butter is more expensive, so this is why. Then a way of doing quality control when, for example, let's say you work in industry, in industrial that you're making yogurt or cheese, etc. So milks are collected from different farmers, and then when they arrive to the place, there is what we call a quality control. So quality control, we first measured. So they're like very easy because, you know, people are receiving hundreds of tanks by hour, so they cannot do, so there is a quick quality control. So they measure the density of milk with a densiometer, so they just kind of like a small tool, they throw it in the milk, and they see the density. So the density is an indicator of presence or not of fat. Before, so it's like at the reception, before it goes to other productions, etc. So if they see that it is very liquid and that it has no fat, or it's defectuous, the milk is rejected, so it's returned to the farmer. So a way of adulteration is that when these farmers remove the fat, they add another fat, just to make it rich in fat, and then to kind of substitute the butter or milk fat with another one. In terms of density, because usually they use specific fat, in terms of density, there is no difference. But in terms of fatty acid, there is a difference. So this is how we can distinguish. So milk fat are known to have a short or a medium fatty acid. So it's, they range from C4 to C6, or the medium one, the medium chain, they range from 8 carbons to 12 carbons. The saponification value is around 220. It's an average of 220. It goes up to 230 maximum. That's what I know of milk fat. What these farmers can do, they mix it with cheaper oils or fats that are mostly vegetable fats, and they have carbon chains that are longer. Carbon chains longer, meaning saponification value lower. And this is how, for example, this is the best way to identify if there is an adulteration of milk. So you do it, so you do the saponification and you see. There is one thing. Coconut oil has a saponification value that is closer to milk, because it has shorter, yeah, is it the coconut oil? Yeah, it should be coconut oil. It has a shorter saponification value that is closer. It's about 235 or 237. It's very closer to the milk. But then, these oils are expensive. Yes, they are vegetable oils, so the people cannot, the farmers cannot really afford to buy these to substitute. So this is why, this is just for your knowledge. You need to know why we use it. So another example, iodine. So it's a measure of the degree of unsaturation. Why? So iodine, so we have an iode. When they are mixed, so they are linked, so they are mixed with unsaturated. So the iodine, they link, or they are associated to the C carbon in a double bond. So this association will help us. So this is a titration technique. So this association will help us to identify the unsaturation. So if there is, so if we see that in the titration, so it's a colorimetric test. So if we see that the color changes, we measure the volume of iodine that we added to the solution, and then we can predict the number or the degree of unsaturation. More we have iodine, meaning, so more we add iodine, meaning more unsaturated, there is more unsaturation, and there is higher susceptibility of oxidation. So, for example, if you have 2 double bonds, you will need more iodines to change the color for this colorimetric reaction. So this is why you identify if you have higher amount or more or less unsaturation, and this can help you predict the oxidation. So if you remember, the oxidation is associated with the unsaturation. So this is a kind of a chart. So these are common. So it's people did it a long time ago. So there are charts to tell you the iodine values in each product. So there is a range of iodine values, and you can see. So unsaturated fat are have different IV compared to the saturated fat. So this is the technique. So usually, so we add the iodine. There is a colorimetric changes. So the color changes from uncolored or from pink to dark red, and then we use a spectrophotometer to have a specific measurement of this. How do we use it? So we use it. Why change it? The writing is weird here. So we use it for rapid authentication of edible oils. So for example, you have an oil that is sold as an unsaturated fat, or omega-3 or omega-6 fat, but in reality it is not. So the best way to see or to identify if you, yes or no, you are getting, or you are, so people are receiving, or this, it is true that these are omega-3 oils or omega-6 oils, so is the iodine value. These techniques, because, so these are easy to measure, they're kind of portable tools, so they're kits. They're easily used or commonly used in food industry, by industrials, by quality controllers, and then even people in the government who are involved in quality control. When we talk about melting temperature or melting point, so melting point is melting temperature, so it's the switch from the solid to a liquid. Saturated fatty acids have higher melting points. So as you can see here, for example, they go from 44 degrees to 77 or even higher degrees. These are for saturated fat. So more you have carbons or higher molecular weight is associated with higher melting temperature. So for example, if you have 14 carbon, the temperature is 44 degrees. If you have 20 carbon, it's 77. So, and this is why, for example, saturated fats are solid at room temperature because their melting temperature is very high. The opposite, unsaturated fat, so for the same length, the melting point can drop. So for example, we have C18 saturated, the temperature is 70 degrees. For the same but unsaturated, the temperature can easily drop to, see here, 46 trans. So the trans are solid at room temperature. Oleic acid, the CS1, the melting temperature is 13 degrees. So, this is why most of unsaturated fatty acid, or they are oils and then they are liquid at room temperature because the melting temperature is lower. And then, so for the same length, the melting temperature or point drops, and this increases. Like there is an inverse association between the temperature, etc. So when we talk about melting temperature, and this is what we do in the industry. So we play with, we'll see it later or even next week, we'll play with the saturated, non-saturated, the change, the length, etc. to, if we want to have an oil or a fat that is easily melting or not. So melting can, as I said, change from one based on the length. So here the melting of C18 stearic acid is 70 degrees, while the C14 is 44 degrees. Either if they are as a free fatty acid, like alone, or they are in a triglyceride, this should be the same. So the melting should be higher with higher molecular weight and etc. So logically, we should have a triglyceride that is formed of three fatty acids of steroid should have higher melting temperature compared to the triglyceride. So you may see in books that, for example, stearic acid as a fatty acid is 68, 70. Here the triglyceride, the temperature can drop a little bit. You will see it can be 65, 68, but usually it's the same. But still, it's always higher than the triglyceride of mesuric acid. Okay, these triglycerides vary in the positioning of their fatty acid. So position is very important of a fatty acid. So here we have a triglyceride. We have the fatty acids that are positioned on the glycerol carbon. Here we have 3 positions. So these are 3 glycerides. So there are 3 fatty acids. So we have 3 positions. So we have position 1, position 2, and position 3. And then this is what we call stereoscopic numbering, or SN. You will see it very commonly in fatty acid. So this is where we have. Usually there is a specific configuration of the fatty acid. So we have SN. S2 this is the way how they are represented in in the scheme, or like how they're drawn. So SN, steric numeric, is usually drawn on the left. So this is just to give you an idea. We have triglyceride. Why this position? We'll see why. Because the lipases, either in the digestion or when we're making or in food processing, etc., the positioning of a fatty acid is very important, especially at SN2. SN2 because, for example, lipases, especially during the digestion, this is how, this is the first position that is targeted during digestion. So SN2, and this is why, for example, vegetable fats, and animal fats are not digested the same way because of the position. We'll see it the next time. Because of this positioning of SN position. So when we have, how do we read this? So when we have SN as a prefix, so this is like before the name of the fatty acid or the triglyceride, we can, so if we see it written here, it tells us that the order is in 1, 2, 3 position. So for example, if we look at the top line, so it's STOM, meaning stearic acid at carbon 1, oleic acid at carbon 2, and mesuric acid at carbon 3. Why? Because there was an SN written before. Sometimes, if we just say STOM without writing the SN here, it doesn't mean that the order means 1, 2, 3 carbons. It can be any positioning and any order. So this is why, for example, if there is no SN written as a prefix before, we can have any combination. We can have STOM, MSTO, MOS, etc., etc. So that's why it's important to recognize and to know how to read these ones. And then, obviously, there are different combinations. So here I'm giving you this 6 isomers, or 6 combination of this. There are typical ordering or arrangement of saturated and saturated fatty acid in the triglyceride, and animal fat and oil fat, and plant fats. So here, for example, here, I didn't change, I saw it yesterday, but I didn't want to change it. says SN1, SN, so obviously you have probably seen it. So obviously it should be written SN1, SN2, and SN3. And just because I was copying pasting and I forgot to change the. So for example, when we have plants, so this is the common distribution. You may see exception, but this is a common one. Plant, you have unsaturated fat at the position S2. So this is in 99% of cases. Fat, you have unsaturated fat in position 2. In animals, you have saturated fat in position 2. So this is how we will distinguish between fat, animal fat, and plant fat. To remember, just to remember, so usually we link plant fat as way to beneficial effect, or so plant fat is beneficial, meaning unsaturated, meaning unsaturated is in position 2. So this is the way how, when I was a student, I was remembering this, because we had to remember this. Animals, so we have saturated. Animals, usually we have saturated fat in most of the case, etc. So saturated is the SN2. So you can remember this way. This is how, as I said, I mentioned before, this is why the animal fat and the plant fats are digested and assimilated and absorbed or assimilated differently in the tissue and in our body in general. So because of this and because of the lipases that recognize mainly SN2 positions. So here, I'm just giving you an example of what we can find. So for example, we have cocoa butter. It can be a combination of different fats, but you can see here, SN2 is always an oleic acid, that is unsaturated fatty acid, and the same for animals. So here we have SN2, and then here. And I added these here just so that in the slide you can see them together. I didn't have them on your slides. So this is saturated fatty acid and saturated. But all these informations are in the previous slide, so you don't have to. Okay. So, fat, if you remember, I said there is a blend, they are a blend of crystalline, of solid and liquid. So solid, these are crystalline forms. If you remember, it's the same thing. So form crystalline, etc. So when we talk about fat, we talk about butter, margarine, and lard. These are the most known and commonly used. So how do we identify the crystalline? So it's the amount of solid within the total amount of fat present in the structure. So usually when we have when we talk about fat content, we talk about these specific proportions of either solid into the total fat or solid, it depends on the matrix, or solid within the liquid. So the crystalline structure shouldn't change from one combination from one food matrix to another. Fats are semi-solid, as I said, or plastic at room temperature, and they contain a range of triglycerides. These triglycerides, they can have different melting temperatures, and they depend on their length, the chain, etc. So this is why we can find within the same matrix, we can find, or at the same temperature, we can find either solid or both, liquid and solid fats. So when we talk about solid fat content, so solid fat content is a proportion of a solid in a liquid. So it's a proportion. So how many solid, what's the percentage of solid within a food matrix? So for example, if we have 100, meaning this fat is solid at 100%. And then at specific temperature. If we increase the temperature until specific time point, we'll see that the fat content or the proportion of fat solid decreases. So this is how we identify the melting temperature. So for example, here we have two products. We have product A and we have product B. Product A, so the graph shows the percentage of solid in food matrix, and then here we shows an increase of temperature. So fat number A, it is solid at specific until when we start increasing the temperature until specific temperature. And then it drops suddenly. So it becomes liquid suddenly. While the B, there is a graduation or gradual melting. So it starts melting at, let's say, here we have 30, 40, etc. It starts melting at 30, and there is a proportion that melts at 40, and there is another proportion that melts at etc., etc. So if we have these two products, what do you think, which one do you think is homogeneous compared to the other? Is A homogeneous or is B homogeneous? What do you think? Remember the crystalline of sugar, it's the same principle. Yeah. Yeah, why A? Yes. Has anyone have another option? Yes, so this is most logical because A, it drops suddenly, meaning that all the fatty acid, they have, all the triglycerides, they have the same melting temperature. They are homogeneous, they are the same. So the temperature drops suddenly, while B, it is a mixture of different fatty acids, so different triglycerides, and this is why the temperature is not homogeneous or is not the same and the same. So this is a way how we identify the fat content. And here, I just wanted to give you an example. I like this example. So here it shows, so when making chocolate, so these industrials use different types of vegetable oils, different types of cocoa butter, but they also use different plant-based oils. And then they use a combination of them, so it depends on the product, etc. So the cocoa butter, it has a melting temperature that is ranging from 30 to 37. This is the cocoa butter. And then when it's mixed, etc., within the chocolate, it should have a melting temperature around 37 degrees. So this is why the chocolate, when we put it in our mouth, it starts melting, because the melting temperature. And then they use other plant vegetable oils and fats to make either harder or soft chocolate. So if they want to make soft chocolate, they use fat that have melting temperature that is lower than 30. And this is why, for example, there are chocolates that you put them you just take them in your hand, they start melting. Your hand starts like to be sticky because they are made with fats that have melting temperature lower than 30. And this is why, for example, I think Ferrero Rocher is one of these examples. It has a melting temperature that is lower than 37, and another one. And this is why, for example, it sometimes done on purpose, because when you have this variation in melting temperature, when you put it in your mouth, there is a feeling of cold, how to say, cold sensation. So it's like you feel that you were eating something cold. And this is how they play with the fatty acid. So this is just, next time remember, when you do it, it's just about fatty acid combination. So this is why I wanted to give you this, because I don't know, I just like this example. Where is my screen? Oh, okay. Okay, next. We'll add 10 minutes, and then we can go for I was going to say for lunch, for a break. Okay, so this is what we call the melting temperature. And then melting temperature depends on if it's as I said, the combination, etc. If it's homogeneous and if it's heterogeneous. The same thing as when we talk about sugar, etc. So homogeneous, usually it has higher melting temperature compared to heterogeneous, etc. When we talk about fat, so within this crystalline structure, these triglycerides changes or vary in their degrees of orderliness, or how they're ordered within the structure, or how they're structured. And this is what we call polymorphism. Same as genetic polymorphism, same here, we have fat or lipids polymorphism or triglyceride polymorphism. So what does this mean? The sentence I wrote in English, of course, in English, in red is, you don't have it in your slides. So when we talk about polymorphism, we talk about different ways that a molecule can organize themselves in a solid phase. Here we're talking about solid phase. We're talking about fat in solid phase. So these crystalline or solid phase, they can differ in physical structure, but when they melt, they yield to the same or to the identical phase. So yes, they may have different phase when they're solid, but when they melt, they are liquid anyway. It just depends on the melting temperature. The triglycerol, the crystals or these fats or these solid composition, they exist in different forms or different versions of fats. Here I'm citing 3. There are at least 3. So we have alpha, beta prime, and the beta. There is also gamma. In chocolate, there are at least 6 forms. In fat used in chocolate, there are at least 6 forms. So it's different. So let's put it this way. So we have polymorphism fats, and a polymorphism of chocolate is kind of different because there are many combinations, etc. So here we will focus on these 3, alpha, beta prime, and beta. What does this mean? So these alpha and beta, etc., they depend first on their structuring, same as when we have, same as crystalline and amorphous we saw together. The principle is the same. But it depends on the configuration and the conformation of the triglycerol and or the position of these fatty acids within the glycerol backbone. So here, you see there are triglycerols. So I just drew them with three lines. So we have what we call tuning fork. So we have SN1, position 1 and 3, same way, and the position 2 in the opposite. So they can be drawn this way, they can be drawn in the opposite, etc. And we have the chair configuration. The chair configuration, we have either SN1 and SN3 on the same, so the same way, but the SN1 can either be on the side. So this is a chair, but it's chair like left or right. So the SN1 can be either on the side of SN3 or on the side of SN2. And how we identify them? So the configuration or conformation, so either chair or turning fork, they are involved in this configuration. So for example, when we have alpha configuration. So alpha configuration, this is characterized as, so like this drawing, what I drew here, I kind of just copy pasted and I put it in very small and I redraw them there. And this is a vertical turning fork. And so these are, alpha is a random configuration or random packing. And then their configuration at, they are positioned at 90 degrees, an angle of 90 degrees. You will see, you will say, oh, but this doesn't, the top figure doesn't look at the bottom figure. So this is how it is, they are shown, or they are like identified. So when we talk about alpha, it's either the top configuration, and on the bottom configuration, just to show you the angle of positioning of these forks on the chain of the fatty acid. So then we have, remember, alpha is the random one, is the most heterogeneous one. And we have a beta prime. Beta prime, same, is a turning fork, but the configuration is, these are tilted structures. So they are tilted about 70 degrees Celsius. And they are intermediate. So beta prime is an intermediate. And then we have, sorry, and we have a beta. Beta is stacked, these are stacked chairs, and they are tight packing. So the configuration is, the angle are different. And then, so remember, alpha, beta prime, you have the turning fork. The beta is more homogeneous, it has tight packing, and these are chairs, so the chairs are stacked. And because here you see there is a space, I mean, I draw them like just to leave a space between them, just to say that there is heterogeneity, while when you draw the chairs, there is less likely to have less space. So they're tightly packed together. And this is what they make, it makes them more homogeneous. So the degrees is the degree of angle of orientation. It's not the degree of melting. It's not the temperature. So when we talk about stability, obviously, the alpha is less stable than the beta prime, and is less stable than the beta. So here, if we have to talk about melting temperature, what do you think, which one do you think has the highest melting temperature? Which one? Remember what we said. We said homogeneous ones should have higher temperature because they're homogeneous. So it takes time for them to melt. So this is why. Homogeneous ones, beta polymorphic form, are the ones that have highest melting temperature. So usually when we have solids, so oils, so as the oil, they solidify, they go from alpha, so this is the liquid, it's less homogeneous, then beta prime in the middle. So just remember, for example, this is an oil. The beta prime is, for example, the margarine. See, it is solid, but it is easily spreadable. And then here, for example, you have the butter, or you have fat, is solid fat. So here, beta prime is when we talk about industrially talking, especially in bakeries, etc., beta prime is the preferred. So people, industrials, prefer keeping their oils in a beta prime because it's easily easy to handle them. So as I said, in application, baking, when we talk about shortenings, so the beta prime is a desirable, the one in the middle. So we don't want it to be very solid, but we don't want it to be liquid as well. So how do we keep these beta primes? We just add 2-3 slides and we stop. There are different ways of keeping them. You remember when we spoke about the crystallization? And then we said, oh, we need interfering agent. So then they can interfere the crystallinity. Remember? It's the same principle. Just here we call them differently. So if we want to keep the beta prime, we start solidifying an olive oil, an oil. But we don't want to go further. And we know that, for example, this oil, the fatty acid that compose this oil, they can be liquid at room temperature. So what we do, we add emulsifiers. So emulsifiers, so these are compositions that help mixing the, they are interfering agents, let's put it this way, and then they can help keeping the beta form instead of going further to the beta. So when we talk about, one very commonly used is the sorbitan ester. So these are surfactants that fit into the crystalline form. So they go into, it's the same way as an interfering agent. So they enter the structure. So they have hydrophobic region that align with the carbon chain of the fatty acid chain. So this is why. And they have the hydrophilic group that align with the carbonyl group. So because of these, if you remember, emulsifier, we'll talk about it in a few slides. So they have hydrophilic and hydrophobic region, and this is what makes them align or mix between the two regions in specific emulsion. So is it similar to interfering agent? Yes, it is, because the principle is to keep, to avoid go further to make more crystalline forms in the structure. And then when we talk about chocolate, it's another way of how to say it? It's another example of polymorphism, and how this polymorphism can lead to undesirable form or undesirable changes. And one of very well cited and known example is the blooming or the bloom of chocolate. So the chocolate is melt at specific temperature. If the melting is not done properly or at proper temperature, then when it solidifies, it forms this specific structure. So white or gray spots on the surface of this one on the right. So the chocolate will lose the glossy surface. So it's not like shining or glossy anymore. This is due to the transition from one polymorphic state to another polymorphic state, and this is due mainly to the polymorphism of the cocoa butter. If you remember, I said chocolate has about 6 polymorphic states, or version. So this is why it's easy to have these undesirable changes in the chocolate. There are two solutions, either adding emulsifiers or tempering. So tempering chocolate is is controlling the temperature, the melting, and the solidification of the thing. Another example is the enteresterification. So, you remember enteresterification? So it's one way of creating more beta form compared to beta prime form compared to beta form. So we'll take a break and then we can continue with the enteresterification and the other example. So where is my microphone? So what does this mean? Enteresterification. It's just a rearrangement. We have seen this together. Rearrangement of fatty acid in the triglycerol. So rearranging fatty acid within triglycerol or between the triglycerol. So either we move from SN1 to SN2, SN1 to SN2 to SN3, etc. This is inside the triglycerol, or from one to another. You will see in books, for example, food chemistry books and other chemistry books, they call them intraesterification and enteresterification. But the commonly used is enteresterification, either within the same TAG or between the TAGs. So there are two different techniques or reactions of doing this. So either chemical reaction, when we talk about random enteresterification, we don't want, we just want to mix them together. And when we talk about enzymatic enteresterification, we can have either random positioning or a direct position. So we want this specific fatty acid in SN2, or this specific, or remove it from SN2, etc. I'll give you some example. So these are the ways how we're doing it. Why we do the enteresterification? Because we want to change the physical properties of oils and fats. Remember, the enteresterification shouldn't change. This was a question of the exam. Shouldn't change the composition as it is, but should change the form. So it can go from homogeneous to heterogeneous, etc. So it helps, this enteresterification helps increasing the melting point, increasing the solid content, and altering the crystalline structure. It is one of the first used and commonly used and as an alternative way to partial hydrogenation. If you remember, hydrogenation, adding hydrogen to the double bond, so then we will have to avoid auto-oxidation or oxidation of lipids. So this is how we can do it. One of the very emerging topics of use of enteresterification is to use it to make infant formula products with specific 3 TAGs, molecular species, either animals, mainly vegetable oils, and then enteresterification to put them in a specific, or to mimic, put them in specific positioning. We'll see it in a few slides, and to mimic the composition of breast milk or human breast milk. And this will help the fat absorption in infants. How do we do it? There are two main stages. First, we hydrolyze. So we need to bring these ester bonds. Then we esterify. We change the positioning. So either we redistribute fat within the TAG, or we exchange between the TAGs. So there are different ways. So let's say we can, for example, start from one product that is more homogeneous. We see greens in one side and brown in one side, and we can go to more heterogeneous fat. So there we can go from A to B or from B to A. Going from A to B is a random esterification, so they were very well ordered, and then now they are switched randomly. So this is what we call random esterification. And then the directed, if we go from more heterogeneous to more structured and more organized one. Same one, which one? The same question, is it A or B? It's the same question I asked 2 or 3 slides before. Which one should have, is more readily to form the beta form? So the logical should be an A because it's more homogeneous. So homogeneity, more homogeneous are associated with the beta form of fatty acids. So as I said, there are 2 techniques or 2 different ways, either the enzymatic or the chemical enteristification. Enzymatic, we need to use microbial enzymes. These are lipases. So the lipases, they cut the specific, the fatty acid, and they help reorganize, so then they can be reorganized later. So these specific enzymes, they hydrolyze or enterosterify, but they mainly hydrolyze. So the lipase, they mainly hydrolyze, but there are other they can enterosterify. The techniques was developed in the 80s. It provides a cheaper source for confectionery fat to replace cocoa butter. So it's easy to set up and easy to handle. So we need a tank, and then we need to add enzymes. So there is one way. This is kind of the simplest form of, so the enzyme go from one side to another. They're put in contact with the product to enterosterify, and this is how they're enterosterified. Chemical enterosterification, we need to use a catalyst. So the catalyst, there are different catalysts, but the mainly used is sodium methoxide. It involves the hydrolysis and the random redistribution of the fatty acid. So remember, enzymatic enterosterification, it can be directed or indirected. Chemical one is only indirected. It's an old technique. It was developed in the 40s. And it was used mainly to modify the solid fat content of lard to improve its portability and baking properties. So this is the first and main use, and then they started using it differently. The setting is different. Here, this is one of the simplest settings, but like it needs more complex installation in the industry, etc. So usually there are different tanks. One is a catalyst, and one is the oil, and then one is a mixture, etc. So this is why it is not easy to install, and it is higher or more expensive compared to the chemical ones. How do we do this? So first, let's start with the directed one. We want specific organization within the triglycerides. So we first hydrolyze. So we have, for example, this combination, saturated and unsaturated fatty acid. We need first to hydrolyze the triglycerides. So what we should do, we increase the temperature. When we increase the temperature, they melt, and then there is then we add the catalyst. The catalyst will just break these ester linkages, and then we start dropping the temperature. When we drop the when we drop the temperature, dropping the temperature meaning solidifying one fatty acid compared to the other. So when we drop the temperature, let's say we increase it at 90 degrees, and then we drop it at 70 degrees. 70 degrees is the one they can solidify at 70 degrees, so they're kind of put aside or remove it, and then we repeat the cycle. So we kind of get rid of these ones. let's say, saturated fatty acid at 70 degrees Celsius. And then we end by having, and we repeat the cycle. And then so on until we, so when we say get rid of it, it is kind of put aside to be reorganized differently. So this is how we play. So we play temperature up and down, different cycles of temperature. When we add, and this is how we change the, we direct the, we go from more heterogeneous to more homogeneous. The other way, so it's the same. So if we go here, first we went from more heterogeneous to homogeneous. Here we're switching. So we're going from the other position. So what we do, same, we need to hydrolyze the triglyceride. We re-acidify at higher temperature. Then they become all liquid, and we keep doing this. So there is a randomization. So when we go to the opposite direction, we don't need a specific ordering. It can be any order. They can be put together. These fatty acids, they can be put together, re-acidified. So we don't have to control this. Then another example. So as I said, we go from homogeneous to heterogeneous, or we go from heterogeneous to homogeneous, either directed or indirect. Another way, use of interacidification is for the as I said, as an alternative of partial hydrogenation. Hydrogenation is adding hydrogen to the double bond. So then, instead of having unsaturated fatty acids that are oxidated easily and doesn't keep the good quality of food, we hydrogenase and we have, for example, fat, so usually solid fat, but there is a problem with the trans fats, as I said. So how we do this? We interacidify with saturated fat here. Saturated fat that we know that it is not a trans fat, obviously. So how we do it? We just mix. This is a random esterification. We cannot control it. So it is a random esterification. So we mix it with a fat. We change the temperature, and there is a conversion from oil to a plastic fat. So this is how, so we're mixing the fats together to obtain different triglycerides, and this is how we can play with the consistency of the fats. How we do use this in the food industry? There are different uses. So for example, one of the uses is in meat technologies, so where plant oils or vegetable oils are used to substitute fat from animals that has been linked to different diseases, obesity, cardiovascular disease, etc., etc. So then an option, the good option was to substitute. So either, for example, can be replace animals in the meat butter and either meat product. The problem is that if the oil are used as they are first liquid. They have different colors, and they don't react the same way as a fat. So if we use it as they are, we don't obtain the right texture, and we don't obtain the right color. The best way is to interacidify, and then have them. So when we interacidify, we mixed the fatty acids. So then we change the melting temperature, and then they become more solid. So either we go from alpha polymorphic to beta prime or beta, and this will help making food at a texture and a color closer to the product that is made with animal fat. It is healthier, and it decreases the susceptibility to liquid lipid oxidation, And it has, as I said, desirable color and texture. Anti-acidification can be used human bias. I spoke about human milk. So human milk, it is a combination of saturated and unsaturated milk. So saturated, if you remember, the saturated of animal milk, animal fat is always in the middle in the in SN2. Here we have the palmitic acid as SN2, and we have unsaturated fatty acids, linoleic acid and alpha-linoleic acid in the positions 1 and 3. So this is how the milk, human milk, is characterized. Human milk is easily digested by infants because they have the lipases, the specific, and they have some gut bacteria that are involved in the hydrolysis of, or the digestion of milk. However, because of many reasons, breast milk or human breast milk cannot be available, cannot be used for all infants. So there was a way, to replace it with the use of infant formula. Infant formula milk, infant formula are usually made with vegetable oils. Vegetable oils, they don't have the same position, the same structure as breast milk, obviously. So they have palmitic acid rather than being at SN2, it is SN1 and SN3. This repositioning of palmitic acid and repositioning, it was associated with the calcium deficiency. Why? Because the calcium, it was kind of, with this saturated fatty acid, it was kind of precipitating or making kind of a saponification, precipitating. And then with the action, so there was kind of a precipitation or reaction between the calcium of milk and the fatty acid, with, in addition to action of the lipases that are present in infant gut. So this was what makes them lead to calcium deficiency in infant. The best way was to replace it, to have human milk substitute or human fat, or human, what we call human milk fat analogs. So these are called next generation fats or structural lipids. And so the way how we can do them is through the interesterification. I'm giving you 2 examples, and these are not the, you may find other examples, but I'm just giving you 2 examples of kind of what, this one was published last year, it was one of the recent one. And so here what they did, they mixed it, first one, they mixed palmitic oil with an alpha-linoleic oil, which is an unsaturated fat, that was made from a specific, this was a specific study, from a silkworm insect. So, and this was, this was kind of an emerging studies using this specific oil. How they do it? So they had palmitic oil, alpha-linoleic oil, they mix it together, and so 2 oils, they interesterified to obtain this mixture. Saturated fat, palmitic acid in the middle, and then unsaturated. So this mimics the human milk. Same example here, what they did. So the first oil is the canola oil, and they used the lard. So this was a specific study. They interesterified at different temperature, and they look at the composition. So this is a way how to use interesterification in making. So why do you think there is an enzymatic? They use it in, both of them, they use it lipases. So here it's lipozymes, and here it's a lipozyme error. So these are lipases. I think they're extracted from beef or from pork. I don't remember. From animals, one of these 2 animals. Why do you think these are enzymatic and not chemical reaction? What? Tell me. because they are ordered, they are directed. We need specific. You remember I said chemical, it is undirected, so it's kind of random enterification. For enzymatic, it can be bought, but then here it's directed. So we need specific positioning of a palmitic acid at the SN2 to mimic human milk. How about emulsions? Emulsion, an emulsifier, so we have seen this in the previous lecture. So these are discrete particles that are dispersed in a continuous phase. So it can be either oil in water or water in oil. So these emulsions, they have lower stability. So because oil and water cannot be mixed properly, so they're easily separated. The best way to do it, to stabilize them, is to use the emulsifier. So here, we have seen this previously, oil in water or water in oil. So what are these emulsifiers? We also call them surfactants. So these are amphiphilic molecules. They contain hydrophobic and non-hydrophobic or hydrophilic groups, or polar and non-polar groups. So they can be attached to both liquid, lipid or oil and water part of it or phase. They are considered as additives, that they promote the formation and enhance the stability of emulsion. They provide technical benefits. Viscosity, they reduce, they change the viscosity. We can have this emulsion as a complexation with starch or starch complexation, and they can help inhibiting the crystallization or reducing the crystallization of fat. So, as you can see here, we have non-polar units here that they can be attached to the oil, where the polar ends, they have the repulsive charges, if you remember. We saw that last time. They're repulsive, so this is why they cannot be attracted. They are repulsive, they are rejected from each other, and this is why they stabilize the emulsion. Non-polar units, these are derived from fatty acids that they have higher than 16 carbons. Short chain lengths can make excellent emulsifier, but can react with water to produce soapy and undesirable flavor. So when we are making emulsifier or choosing emulsifier, we have to be careful in choosing the right length, so to avoid the hydrophilic rancidity. So when we talk about emulsifiers, we also talk about HLB or hydrophilic hydrophobic balance. So this is kind of a relative size of hydrophobic and hydrophobic section of an emulsifier, that these sizes of that they determine its behavior. So either an emulsifier can be used as an emulsifier in water-oil emulsion or in oil-water emulsion. This depends on the size of the hydrophilic and the lipophilic proportion. So a more lipophilic emulsifier can be used or is used in water in oil emulsion, and we have the inverse. So these are the examples for phospholipids that are commonly used as emulsifiers in food. When we talk about emulsifiers, so as I said, mostly we use phospholipids because they are easy to get and they are cheaper. Phospholipids can be found in soy lecithin. So this is a byproduct of, we'll see it next week, of soybean oil. So when we make, lecithin is during the processing of or making soybean oil, we can obtain the lecithin that can be used as an emulsifier. eggs are also a good source of phospholipids, and they use it as an emulsifier. Monoglyceride, and then sodium sterol lactylase. So if you remember, we said this was is also used in to avoid the staling of bread. Then we have the sorbitan ester. If you remember, we saw it in the previous slides. So they prevent the crystallization of lipids and preserve the beta form. Why they preserve the beta form? Because these are lipophilic emulsifiers, so they have a long chain of hydrocarbon here, and this is what helps stabilizing these structures or keeping the beta form specifically. The gums and starch are used as emulsifier. They mainly, I know I keep saying this, so I don't really like, when I talk about starches and gums, I don't, so these are long polysaccharides I don't really like talking about emulsifiers because they're not really, by definition, they're not really emulsifiers. They are thickening agents. But because they help stabilizing this emulsion, this is why there are some, you may even find this in books, they are kind of categorized as an emulsifier. But they are not. They are thickening agent or a gelling agent. So these one, they thicken or gelatinous continuous aqueous phase in oil and water emulsion, and they can do the opposite for this. So it can be used for both, water and oil or in water. So let's have this example. So we have a fresh dressing, French dressing, or salad dressing. It's water in oil emulsion. So it has canola oil. This is a recipe. Canola oil, vinegar, mustard flour, paprika. It has xanthan oil. Xanthan gum is a polysaccharide. It has polypropylene glycol alginate and spices and EDTA. So what do you think? Where do you think is the emulsifier? Any idea? Random. You'll be surprised. You'll be surprised to know which one is the emulsifier. Guess. Any guess? Yeah, I remember last year someone guessed it. One. I remember they were in the top. Okay. The mustard. So this is why, for example, when we make dressing at home, we add mustard and then we just kind of mix it, and to be able to keep this not separated. Paprika, yeah, paprika, because it has a specific structure. This is why it's used as an emulsifier. Paprika is also used as coloring agent because it's red, and it is also can be also used as antimicrobial. Although the AW here is not that high. Which one is stabilized, can be usually used as a thickening agent, stabilizer? Polysaccharide. Yeah, xanthan gum and the alginate. Alginate is a polysaccharide. EDTA is a chelator agent. So it helps, it avoids the auto-oxidation. Spices are okay, so for flavor, but they're antimicrobials. Sugar, it's for flavor, but it also reacts with this. Okay, how about this one? This is a mayonnaise. This is kind of a recipe of mayonnaise. So having salad oil, vegetable oil, we have lemon juice, egg, egg yolk, and so we mix thoroughly, or we use either manually or a mixture, and then we keep adding oil slowly until we form this consistency. Oh, this supposed to be a question. What was it? Is it an oil in oil or oil in water emulsion? This is an oil in water. I know it doesn't make sense, but it is oil in water because the oil droplets that are crumpled or packed into a very small amount of water. Here there is almost no water. Like the water is coming from the juice and the oil, which is not really. So it's the oil is their droplets. See, there are two small amount of water. Within this water, we have droplets. It's like kind of putting a big volume into a small volume. And this is why we have to keep mixing. Egg function is emulsifier. So why we add the oil slowly and we beat the oil very high? Because of this, you don't have it because we're supposed to. Why? We need to really mix because we need to break down the oil into very small droplets because these are the droplets that are dispersed in very tiny, small amount of water. So we need to like break these droplet oils, and that they can mix it because we're mixing with the egg, that they surround these droplets and stabilize the emulsion. And the water also comes, little bit of water comes from the eggs. So see, this is why we have to mix. I give you, it's interesting. I really encourage you to go and look at the industrial margarine. Margarine is something like a butter. So it's a water in oil. Here I am giving you example of different types of margarine. So we have, this is the regular one, Bissell one. It has 70 calories per serving. So it's constituted, it is mainly made of 75% of oil, less than 16% of water. It has soy lecithin as an emulsifier, and vegetable monoglyceride as another emulsifier, and the potassium sorbate as antimicrobial. Then we have less calories. One with less calories, one with less oil or less fat. So, because it has to be, preparation has to form 100%. So instead of having 75% of oil, we have 58% of oil. So we increased the number of oil, the number of water. If we want to have fat-free or less fat. So in this case, we increase the amount of water, we reduce the amount of fat or oil, but then if we keep it like this, it will be kind of a liquid and very viscous. So what we need to do, we need to add thickening agent and emulsifier to keep the structure. So if you go to the market, you may have it at home, etc. So based on the margarine, either the like regular one or the one with lower calories, they should have the same consistency. The color is a little bit different, but the consistency is the same. So how we do it? How it's done here? They added the gelatin. Gelatin is a gelling agent. We'll see it when we talk about the protein later. And they added the whey protein, same. They have the lecithin as an emulsifier and a monoglyceride. So in this way, they added the gelatin as a gelling agent. They could have added the, so as I said here, it's like these are the combinations. They could have also added starch, for example. Starch is a gelling agent or a thickening agent, as I said here in the example. So here, it's even lower calorie, so they even increase it going from 58 to 68% of water. And they added the gelatin the same way, but they added rice starch. So this would have to thicken or to make this droplet thick. And then the consistency between 70, 35, and 25 calories per serving shouldn't change. So this is the way, kind of a schematic representation. So we have droplets of water and droplets of fat or fat crystals, and then that are put in a specific structure. And because this is kind of a gel or homogeneous, we have a liquid oil, an emulsion, we have a liquid oil that is also distributed. This was an animation, so this is why I couldn't add it in your slides. So the principle, this principle of adding water, decreasing oil is applicable to in other products. So lower the fat, and then to be able to lower the fat, you need to increase the water content, but you need to add a thickening agent to keep the consistency of the product. This is a rule, especially when we talk about fats and ads. Okay, mayonnaise. Mayonnaise, we have another example. So we can have regular and light. When we talk about light, it's the one that has less oil and less calories. For the light one, the modified cornstarch is added to keep it thick, or to keep this consistency. So if you, as I said, we always try to play with the ingredients. To we add either the gelling agent, gelatin, for example, or specific starch, or we add thickening agent here as a starch. How about fat replacers? The name says it. So they are used to replace fat in products with high fat content. Now, for like health purposes, nutrition purposes, etc., we need to reduce fat content. So fat replacers are used in frozen desserts, processed meats, cheese, and sour creams. There are two categories. They are what we call fat substitutes and fat mimics. Fat substitute, it substitutes the fat. So it has a structure that is similar, because we need to substitute, just remove and replace. A structure similar to the THGs. It substitutes the fat on a basis of 1:1. So if we remove 1 gram, we replace it with 1 gram. It has to possess the same structure, physical structure, and functional characterization as the fat. So then it is so that consumer don't see the difference between the real fat and the fat replacer. Usually these fat substitutes are synthetic, so they don't have any energy added to the food matrix or to the food product, or energy or no energy or calories added. And so they maintain the palatability because they substitute. And they are supposed to reproduce the texture and the mouth-feel of fats. They may not reproduce the taste because these are synthetic, so we cannot, there is no guarantee that we have exactly the same taste properties. Fat mimics, they mimic the organoleptic and physical. They cannot replace the fat molecule in weight-to-weight basis. So these are not replaceable. They have energy contribution because the kilocalories per gram of food, they can range from 0 to 4 to even higher. And these one, they replace the mouthfeel of fat. They have usually these compounds, they increase or they have greater viscosity in the mouth, and they cannot substitute so same as here. So here we substitute the fat in 1 per 1. Here we cannot because they're kind of mimic this one. Fat replacer. So this is what we call the new generation of reduced fat foods. There are 3 types. There are lipids, proteins, and carbohydrate bases. So we can replace them with other lipids, with lower calories, with other proteins that can mimic, and with carbohydrates. So usually when we talk about fat substitutes, these are lipid fat replacer, because if we want to substitute, we want to remove one and replace one substitute, it has to be fat, it has to be a lipid-based product. For the mimics, they can be either protein, carbohydrate, fat replacer. It doesn't really matter. And you can see how the science or how the technology is emerging. And you can see the product or the million in the market, so like million in US dollar in the market. So how they are progressing, all the fats. So either carbohydrates, and you can see here the carbohydrate-based are the ones that are used because so they can use starch and they can use other constitution. They're easy to make and they're easy to handle compared to the other ones. Here, this is an example. You don't have to remember this. So this is an example of carbohydrate. So for example, we have a full fat. So the yellow circles are fat. So full fat, you can see this is the food matrix. You can just imagine we have different molecules, different combination. If we remove the fat here, the texture won't be the same in all. So either concentrated liquid, semi-solid when we talk about yogurt, or dry solids, for example, the shortbread here. Then, if we want to have a substitute that are carbohydrate-based, we need to make kind of granular carbohydrates, or either like long chains of carbohydrate. Why? Because these we need to have the same consistency. For example, if we want to make a fat replacer, we need, in yogurt, we need to remove the fat, but put back, for example, a modified starch, so then they can keep the consistency here of the fat. So, as I said, we can have granule and we can have linear or long chain. If you remember the granule of the starch, so this is where we can find them here. So this is an example. Protein by the microparticles. I hope we have time for the protein microparticles, and this is kind of something very interesting in the food industry, microparticle. These are mainly derived from milk and eggs. These are particle-sized proteins, powder, reduced in different sizes, in smaller size, and has spherical shape. So they are kind of a sphere, very small, and they can be easily. So these ones, they are protein-based. They are mainly used in ice milk or ice cream, etc., because they are heat sensitive. Because they are protein, they cannot be heated. If they are heated, the protein is denatured, so it doesn't have the same function and structure as before. So this is why we cannot have it. Have it. So when it's added to the ice cream, for example, it helps increasing the viscosity and the creaminess of the, and it simulates the creaminess or the creamy structure that is made with the fat. They are supposed to have lower calories, lower in calories, so 2 calories per gram of ice cream, for example, compared to 9 if they were fat. Lipids, so this is what we call structured lipids. These are emerging technology structured lipids. So these structured lipids use the technology of enterification to create oils with triglycerols that have short and medium chain fatty acids and contents. So we need, so the length of fatty acids the fatty acids are shorter than the natural oils. So they're supposed to have lower caloric intake. And it's just kind of through the way how it is. So it's an intensification, and it's usually microbial intensification because we need a specific one. How about lipid oxidation? It's lipid rancidity. This is how we call it. So, when we talk about lipid rancidity, also refer to the deterioration of fat. So the fat is deteriorated, is no longer good enough to be consumed. So it results in the formation of compound that are responsible of flavor and aroma of product or fat. So there are two deterioration. There is an oxidative rancidity, that is the most common one, and there is an hydraulic lactic rancidity. It is well, so this rancidity, it is one of the well-studied phenomenon or deterioration because it happens in very often and it plays a role in different foods. It happens in different foods, sorry. And the oxidative rancidity, because it's oxidative, so it involves a reaction with an oxygen. So the oxidative rancidity, it can be due either to an auto-oxidation, this is what we will be talking about, and then the photosensitization. So I give you the example of photosensitization, but these are extra slides just for your knowledge. I didn't want to skip this. I won't be covering this in the lecture, but I gave you the slides just for the extra slides just for your knowledge. The photosensitization is a reaction molecule oxygen with lipid via light catalyzed reaction. So when the oils are exposed to light, so this is where photosensitization happens. Oxidative rancidity, yes, it's very well studied, but it's very hardly or very difficult to study because it's very difficult to study a rancidity or the oxidation within a food matrix. So this is why researchers, they created they call model systems. So these are single unsaturated fatty acid that they are used in different types of reaction to measure the rancidity. The rate of rancidity is measured by different techniques. Usually it is measured at 25 degrees, and then the rule or the baseline is 25 degrees, and then this is what we consider as 25 as a room temperature, and then that can change from one to another. So this is kind of a chart of auto-oxidation. Unsaturated fatty acid, obviously, they have zero alkylase group, so they don't have free radicals to oxidate, and they cannot, for example, if we do this, if we use the model system and we incubate the fatty acid at room temperature, there is no oxidation. So here, non-saturated, this is given an example, non-saturated has an oxidative rate of 1. There is no oxidative rate. Then, unsaturated one, so unsaturated, for example, you have one double bond, one alkyl group. It takes 82 hours for this oil to oxidate or to start oxidating at room temperature. More you have double bond and more you have unsaturated, faster is the oxidation happen, and higher the oxidative rate. So this is, see here? So you have 82 hours in this 18. So the alpha-linoleic acid, for example, this is the main fatty acid or main fatty acid omega-3 fatty acid in flaxseed oil, and it takes 1.3 hours to oxidize. So for example, if you have your for people who take or eat flaxseed oil, so usually people grind it. So if you grind a flaxseed oil, you have to store it immediately, covered from the light, and at 4 degrees at least, to avoid the oxidation. Otherwise, the oil is oxidated and is not helpful anymore. So this is how we, and this is how we set, for example, the not only the oxidation rate, but the storage, etc. Then there are different factors. So it doesn't only depend on the double bond and the length, but it also depends on the amount of oxygen present. So high level of oxygen will influence presence of antioxidant or pro-oxidant. So antioxidant, they stop the oxidation. Pro-oxidant, they just enhance the oxidation rate. So pro-oxidant, these are metals mainly, and this is why we so for specific unsaturated oil, we avoid storing them in metal structure or container because it increases the oxidation. The temperature, as we showed, and water activity. So here we'll just go fast through like the steps. So there is an initiation. There are oxidation. They go through 4 steps: initiation, chain propagation, chain branching reaction, and termination. So let's start with the three first. So when we talk about initiation, so the fatty acid here, you remember this formulation? Fatty acid. Then the hydrogen is abstracted from the fatty acid to yield to a free radical. So R point is a free radical, and this radical combined with n-paired electrons, so easy to react. These are odd numbers of electrons. So this happens near to the double bond, obviously, because we were talking about unsaturated fat. The reaction is very slow. It happens slowly, but it can be catalyzed by light and metals. Then, once we have this free radical, then there is an addition of oxygen because we're talking about oxidation. I know some people may have exams, so feel free to leave if you want. Anyway, I'm recording, so no worries if you have to leave because I think some of you have an exam this afternoon, okay. So then there is a formation of what we call peroxide radical. And this is a chain reaction. So this kind of continues, and this is what we call the propagation. So it's one radical, and it keeps going. And then, because of the formation of these hydroxy peroxides, and these are odorless and tasteless compounds, they don't contribute to the deterioration, this intermediate, but they are unstable. So they contribute to what we call the branching chain reaction. So these are kind of a product for another reaction. So here, when we talk about, so these are hydroperoxide, and they keep going with other reactions. So this is what we call chain reaction reaction. They involve the breakdown of the hydroperoxide compound into free radicals. So the product that result of these reactions here, they're volatile, and they are responsible for the off flavor and the odors. These products are mainly ketones. They can be formation of alcohol as well, and the aldehyde. Aldehyde, I use it as markers of oxidation. So if we want to measure the oxidation, we can measure the presence of aldehyde in the contents. And then there is the termination. So formation of a compound that is not a free radical. So there is no free radical anymore here, as you can see. So R goes R together, etc. So one free radical, it represents 100 100 hydroxy molecules. So the products are dimers, and there is an increase in molecular weight and viscosity of rancid oil. So because of all these changes, there is changes in molecular weight, and which leads to the increase of viscosity and the changes of flavor. As I said here, this is I'm not covering. This is just for your knowledge, so then you know. I forgot to put extra slides here. So this is for your knowledge. So whenever I put extra slide, meaning it's just for you to, if people who are interested, etc. So how do we prevent the rancidity or oxidation? So we need to add antioxidant. Easy. There are different antioxidants. So as I listed here, one of the very well-known, etc., is the tocopherol or vitamin E. So these are naturally occurring in many plant oil. They react with the free radicals to become free radicals themselves. The vitamin E free radicals is deactivated by oxidation to quinone. So it's easily added, easily obtained, and easily reacting to stop the reaction. How we do this? As I said, it's the react. So the AH, it becomes itself reacting with the alkyl radicals to stop the reaction. So here, the vitamin E is an AH here. And as you can see here, there is a change in the, so this is the peroxide value. Peroxide value, PV peroxide value is the way of measuring the oxidation. So and as you can see here, the peroxide value becomes very high when the oil is alone, while the antioxidant, it delay the starting of the oxidation for a specific time, and it goes out. So this is why we need sometimes antioxidant to avoid this one. Then there is action of these antioxidants. They can act differently. So either by what we call quenching or attracting. So single oxygen can be quenched, or like kind of a trap. And the quencher, they can be beta carotene, they can be lycopene, they can be other components. Or they are chelators. So we chelate. So usually citric acid and mostly EDTAs are used. EDTAs are chelators. They inhibit the oxidation by chelating the metal that catalyze the auto-oxidation and the photosynthesization. So chelators, they attract or they trap the metals that they don't react or they don't get involved in the reaction, or they help speeding the reaction. So remember this, the chart of water activity. The lipid oxidation, it's a little bit tricky. So if you can see here, the curve of lipid oxidation goes from higher, very high, when they are, it's a very low AW, and then goes down and then goes up again. So this is the lipid oxidation, because there are different ways. So the oxidation can happen in a very dry product, or a very wet or liquid, or where the AW is very high. You remember what is AW, right? I hope. So here, for example, around 0.3 to 0 up to here, there is what we call the removal of surrounding lipid hydroxide. So there is an increase of oxidation because of this non-availability of water. And then when the AW is within the range from 0.35 to 0.6, there is an increase mobility of metal and oxygen. Because we are in the range where the oxygen is easily mobile, there is an increased mobility, and there is an increased mobility of oxygen, and here, and within this range, we have an increased. It's kind of opposite of, for example, microbial growth. And then goes up, there is a dilution of metals and oxygen. So here, AW, water is more available for reaction. And then, but there is kind of a decrease when, here. You see here? So it goes up, and then the water is more available, but there is a because water is more available, there is a dilution of metals that catalyze this oxidation reaction. So this is why we have, it's going back to the decrease of lipid oxidation. So lipid oxidation is a little bit tricky when we talk about AW or water availability. So here, this is an example of how we can use, it's an old study, but I liked it because it has sensory analysis, etc. I cannot see. Okay. So here, this was a study. This was a study where they studied the effect of adding natural oxidant, natural product as an antioxidant, and to increase the stability of cooked and refrigerated meat. Meat, because it contains higher level of fat, so it can be easily oxidated. So what they did, so they took beef patties, they prepared with different antioxidants, they cook it, wrap it, and they store it at 4 degrees at different time points. And then they evaluated the sensory analysis, because the oxidation, if there is an oxidation or auto-oxidation, meaning there is a rancidity. And they also used another test that is called the T-bars. T-bar stands for 3-barybutyric acid reactive substance. So this is a colorimetric test, as shown here, and it is used to measure the lipid oxidation and oxidant activity. So darker color, meaning there is a higher oxidation. Antioxidant user, they used rosemary, grapeseed, and oregano. So these are the ones that we all use at home. And then I like this. The reason why I am using this old, because they use it. Remember, what is this? You remember? This is a spider plot. Sensory analysis. This is kind of one of the components of a spider plot. So what they did, so they had different products, different antioxidants. They used rosemary, they used grapeseed, they used oregano extract at different concentrations. And they first tasted or tried 5 parameters. Rancidity, as it is, sulfur, because it's a form of deterioration of meat, herbal taste, grassy taste, and were cardboard. It must be very weird taste. So then they compared between them. Because it's with hard, so just for the color doesn't exist in the paper. So as you can see here, and they compared with the control without antioxidant. And then you can see here that the one with control, no antioxidant, meaning the meat oxidated. So the rancidity was higher. The word cardboard, like weird taste, was higher, etc. The one with the lower grades was the rosemary. And this is why they said, okay, the rosemary is the one that helps maintaining the quality and is a good antioxidant and or effective antioxidant and can be used for beef. And they also use the T-bars. The T-bars, because they as I said, these are react colorimetric test. Lower T-bar meaning lower or less oxidation, meaning higher quality or better quality. And then we can see here the control without antioxidant. It has higher antioxidants or higher T-bars compared to the one or to the rosemary or to the grape seeds. And you can see here the oxidation starts increasing over time. And this is one of the, this is how we do the, we do the test. We do the analysis. Okay, we have about 10 minutes, and then I didn't want to put any conclusion. I didn't want to, like, I left the slide empty like this. Because I wanted to hear from you the message of today. We still have 5 minutes to do it, and we can go. So what's your conclusion message today?